Organometallic chemistry അല്ലെങ്കിൽ organometallic compounds, their synthesis, structure and bonding. അതിൽ ക്ലാസിഫിക്കേഷൻ ഓഫ് ഓർഗാനോമെറ്റാലിക് കോമ്പൗണ്ട്സ് കഴിഞ്ഞ ക്ലാസ്സിൽ നമ്മൾ പറഞ്ഞിട്ടുണ്ടായിരുന്നു. പൈ ബോണ്ടർ, സിഗ്മ ബോണ്ടർ എന്നൊക്കെ പറഞ്ഞുള്ള കോംപ്ലക്സിൻ്റെ ക്ലാസിഫിക്കേഷൻ. എന്താണ് ഓർഗാനോമെറ്റാലിക് കോമ്പൗണ്ട് നമ്മൾ പറഞ്ഞിരുന്നു? മെറ്റൽ കണ്ടെയ്നിങ് compounds containing metal carbon bond. Here the interaction may be ionic, covalent, which can be delocalized between one or more carbon atoms of an organic group or molecule, or a transition or lanthanide, actinide or main group atom. And the basis of classification we are already discussed. Here the organometallic chemistry can be viewed as a bridge between organic and inorganic chemistry. And there are several organometallic compounds are reported. Next we are studying about 18 electron rule, which is an important rule in organometallic chemistry. Here the first attempt to account for the bonding in transition metal complexes was made by Sidgwick, who extended the octet theory of G. N. Lewis to coordination compounds. According to him, ligands were considered to be Lewis bases which donates electrons, usually the one pair of ligand, to the metal atom, which in turn act as Lewis acid. So the ligands act as Lewis bases and the metal atom act as Lewis acid, electron acceptor. And what is the reason for this? The reason for stability of these compounds was assumed to be their tendency to attend the stable noble gas configuration for the metal. Here the sum of the electrons on the metal plus electrons donated from the ligands was called effective atomic number. That we have already studied. Effective atomic number means the number of the total number of electrons possessed by metal and the electrons donated by ligands to the metal. Here, when metal achieves an outer shell configuration of n-1d10, ns2 n-1d10 np6, there will be 18 electrons in the valence orbital of the metal atom and they have a closed stable configuration. This rule is known as the 18 electron rule. And this rule is obeyed with a high frequency by organometallic compounds. Organometallic compounds are more frequently obeying this 18 electron rule, especially those having carbonyl and nitrosyl ligands. It is also act as a useful tool for predicting formula of stable compounds. So they are found to be application in many applications in organometallic chemistry. Then molecular orbital theory and 18 electron rule. In some complexes, the 18 electron rule is not strictly obeyed. That is, the complexes which are stable and with more than and a fewer than 18 outer shell electrons are common. In some organometallic compounds also, there is electrons less than 18 and more than 18 is observed. In such case, 18 electron rule is not obeyed. Organometallic compounds and the 18 electron rule, that is a basis for rationalizing the exceptions, can be gained by reviewing the molecular orbital description of bonding complexes. The most stable arrangement will be that in which all the bonding orbitals are fully occupied and antibonding orbitals are empty. We know that we have already studied in the coordination chemistry that when a metal is under the influence of an electric field and under the influence of a field, it is splits into two sets of orbitals and T2G set and EG set. T2G set two sets, bonding set orbitals and antibonding orbitals. Bonding orbital includes A1G, T1U, EG and T2G. If all these orbitals are fully occupied and the antibonding orbitals remains empty, in such case the 18 electron rule is observed. Since there are 9 bonding molecular orbitals, this will require 18 electrons. Here A1G means 1 orbital, T1U means 3 orbitals, EG means doubly degenerate, that is 2 orbitals, and T2G means 3 orbitals. Totally 9 orbitals are there and each orbital carry 2 electrons. So there is totally 18 electrons in their bonding orbitals. So they are found to be stable and obeys 18 electron rule. And these complexes will therefore tend to adhere the rule if they have large delta zero value, that is band gap, large gap, that is bonding delta zero means it is the band gap between bonding and antibonding orbital set of orbitals. If the delta zero value is very high, this means that all electrons get paired in the bonding orbitals and obeys 18 electron rule. And the complexes included in this category are complexes of second and third row transition metals, which are never found to have more than 18 electrons beyond the core of molecular orbitals. There may be fewer than 80 electrons. However, the ligands do not provide stabilization of T2G level by bonding, sigma bond, pi bonding. The complexes like tungsten tetrachloride, that is contains 40 electrons, tellurium fluoride contains 50 electrons, osmium chloride contains 16 electrons, platinum fluoride contains 70 electrons. In such case, these complexes do not obey 80 electron rules. Ligands such as carbon monoxide, nitrogen monoxide, and which are high in the spectrochemical series because they have good pi acceptors, are very effective at stabilizing T2G orbitals. This leads to a large delta zero values and increase in total bonding energy. As a result, octahedral carbonyl and nitrosyl complexes are found to be seldom depart from 18 electron rule. In case of octahedral complexes, if there is CO and NO as the ligands, they will act as good pi acceptors. In spectrochemical series, their value, delta zero value is very high, so they can act as good pi acceptors. As a result, they will stabilize T2G orbitals, and hence all the electrons will filling in their bonding orbitals, so they found to be obey 80 electron rule. If delta zero value is small, what happens? The electron may occupy in antibonding orbitals also. The occupation of weakly antibonding orbitals is also possible. As a result, stable complexes with 19 electron, 20 electron, 21 electrons, 22 electrons are also found to be possible, and they depart from 18 electron rule. In the case of a tetracarbonyl nickel, the 4 sigma bonds from carbonyl groups result in 4 strongly bonding molecular orbitals, that is A1 and T2, accommodating 80 electrons. Means that 6 electron in T2 level and 2 electron in A1 level. So they totally accommodate 80 electrons in their bonding orbitals. The remaining 10 electrons must occupy the E and T2 star orbitals, which are the anti-bonding. Formally here the non-bonding and anti-bonding orbitals respectively. Here the E orbital is a non-bonding and T2 star orbital is the anti-bonding orbitals. Since delta T value, that is for octahedral complexes it can be written as delta O, for tetrahedral complexes it can be written as band gap is written as delta T, and in tetrahedral complexes delta T is very small, occupation of antibonding level is not energetically costly and the complex is stable. With only 4 ligands capable of contributing 2 electrons each, any tetrahedral complex in which metal has fewer than 10 electrons available obviously will have fewer than 18 electrons in a total in the molecular orbitals. This means that thus in tetrahedral exceptions to the 80 electrons such as the stable 30 electron species are quite common. So this rather than 80 electron rules, the complexes are found to be more stable in the tetrahedral complexes even though they do not contain 18 electrons. Square planar D8 transition metal complexes are consistent exceptions to the 18 electron rule. The combination of 8 metal d electrons and 2 electrons from each of the 4 ligands gives in the case of D8 or D8 complexes with the D8 configuration. There are 8 electrons for metal, means that 8 electrons there, and 4 ligands, totally 8 electrons also from 4 ligands. Then total electron is 8 from metal and 8 from ligands. So totally 16 electron. These complexes possess such high stability that it is often said to obey a 16 electron rule. With 60 electrons, all the bonding molecular orbitals in a square planar complex are occupied. Any additional electrons would have a destabilizing effect because they would occupy antibonding orbitals. The addition of one ligand could convert square planar complexes into a 5-coordinate 80 electron complex. Yes, and in fact 5 coordinate complexes such as NiCN53 are well known because of their extra stability. That is, a 60 electron complex will converted into an 80 electron complex by addition of one or more ligands to a square planar complex. So they will converted into a 5-coordinate complex. In general, the conditions favoring adherence to the 80 electron rule are an electron-rich central metal and ligands that are good pi acceptors.